This problem provides us with a circuit that has a PMOS, an NMOS, and a DC voltage source, and asks us to design the stage for a power budget of 2 milliwatts, ensure that both transistors remain inactive, and calculate the output impedance. So we have our circuit set up in LTspice, and a couple of things to note for the PMOS. When we get it from the component library, it is oriented in the incorrect direction. So we need to make sure to type Control E, Control R to get it oriented properly. Also, when we do our SPICE directive to specify the parameters for the PMOS, we have to be sure to include this p-chan parameter here. So with our setup, we will begin by drawing the small signal model and calculating the gain equation. So in the end, we'll have a sine source here. So we can begin by drawing the sine source, and then it goes directly to our NMOS MOSFET. So we'll have VGSN, and then our dependent current source, which is GMN, N for the NMOS, times VGSN, and then R naught N. And the drain for the NMOS goes directly to the drain for the PMOS, which is the opposite of the NMOS. So we're just going to draw the same small signal model, but flip the other direction. So that's going to be R naught P, and our dependent current source, which is GMP, VGSP, and then over here we have VGSP, and that goes to ground, because when we draw a small signal model, we short our DC voltage sources to ground. So because that goes to ground, that means that we also have ground for the VGSP voltage is just ground. So that voltage is 0, and that means that this current source is 0. And V out is right here. So our gain is V out over V in, and that equals current times resistance, and the current goes down here, which means that it goes up across the parallel combination of these two resistors. So we see a negative GMN VGSN going from V out to ground. And then we have R naught N in parallel with R naught P. Now R naught N equals R naught P, and that is because R naught equals 1 over lambda ID, and our lambdas are the same as given in this problem. And the current has to be the same because the current, it comes out of this DC voltage source and goes across both transistors to ground. So that means that these two R naughts are the same in this problem. So this is the same as 1/2 times R naught, because R naught in parallel with R naught is 1/2 times R naught. So we can rewrite our gain equation. We'll substitute negative GM for the square root of 2IDKP, and then we have 1/2 R naught. Here where I wrote this VGSN, it was actually V in. VGSN equals V in here, because those are the same. And then I moved it over here. So I didn't quite write that equation correctly, but VGSN isn't in our final equation since it goes over here. We divide by V in, so V out over V in equals the rest of the gain equation. So now we know what our gain should be. This problem doesn't ask for a specific gain, so we will just calculate what the gain is based on the parameters that we are given. So what we are told is that we want our power budget to be 2 milliwatts. So that means that we want 2 milliwatts to be pulled from this DC voltage source here. So P equals IV, so 2 milliwatts equals I, and this is ID, because that current is the same current across that whole thing. And V is 1.8 volts. So we can solve for ID and we get 1.1 milliamps. Now we can plug in 1.1 milliamps in our gain equation, and we can solve for what the gain will be. So that's going to be the square root of 2 times 1.1 milliamps times Kp, and that's Kp of the NMOS, because we're inputting our sine source through going across the NMOS and coming out at V out. So that's Kp of the NMOS, which is 0.022, and then we multiply that by 1/2 times R naught, and R naught is 1 over lambda, which is 0.1, times ID again, which is 1.1 milliamps. So that gives us a gain of 32. So that means that when we bias our transistors and solve this circuit problem, that we should end up with a gain somewhere around 32. So now we're going to jump over to LTspice, and we're going to bias these transistors so that we get 1.1 milliamps dropping across the PMOS and 1.1 milliamps dropping across the NMOS. And we want our DC bias point here at V out to be 0.9 volts, because that's halfway between our voltage rails of 1.8 and 0. So we'll just set it directly to 0.9 volts by putting a 0.9 volt voltage source there temporarily. So that tells us that we're inputting 1.8 volts to the source of the PMOS, and we're biasing it at 0.9 volts at the drain, which means that 0.9 volts is going to drop across it. So now we can sweep our, I can explain that a little better. So we're now going to sweep the voltage source that goes into the gate to bias our transistor properly so that 1.8 or 1.1 milliamps will drop across it. So we're going to do pulse. We're going to do from 0 to 1.8 volts. And we're going to do 0, 1, 0, 0, 1. And that tells us that we want the rise time to take 1 second. We're going to go from 0 volts to 1.8 volts in 1 second. So we can see all the values in between and see what voltage we want to get the current that we want. So we're going to do a transient, and we're going to do it for 1 second, because that's how long it's going to take to go from 0 to 1.8 volts. And we're going to measure the current that is being pulled from this 1.8 volt source here. We want that to be 1.1 milliamps. We need to change our axis, our x-axis here from time to voltage. We want it to be the voltage VN002 is what this one is. The voltage that is going into the gate. So VN002, and we're still measuring the current there. And so we're at 1.1 milliamps at 969 millivolts. So we're now doing a DC value of 0.969. to switch this back to time now. And we'll see that we're at 1.1. We'll go to 0.970. And that looks pretty good. So we're at 1.1 milliamps there. And now we need to bias the other one. And for the NMOS, we're going to go from 0.9 volts to 0. So down to ground. So we're going to do the same thing here. Where we're pulsing from 0 to 1.8. Taking 1 second to do it. And we're now measuring the current that we're pulling from this 0.9 volt source. And we need our x-axis to be VN004. Because that's the voltage that's going into the gate of the NMOS. And we're going to look at 1.1 milliamps again. That's at 704 millivolts. So we'll change this to a DC value of 0.704. And switch this back to time. Since we're not sweeping this source anymore, it's just a DC value. And that's going to give us a current of 1.1 milliamps. So that looks really good. So now we'll put our circuit back together. We don't need this 0.9 volt source anymore because we biased it so that our V out will be at 0.9 volts. So we need to make sure that that's the case. And then we can add our sine source into this circuit. And we want to put this 0.7 volts in series with the sine source. And we can do that. Oops. Adding a DC offset to our sine source, 0.704. We'll add that DC offset to this sine wave. And we need our 1 kilo ohm source resistance as required by the problem. And now we will measure V out. We're going to change our transient to 0.01 because we have a 1 kilohertz sine source. And then we will measure our gain. We are inputting 1 millivolt and we're getting 69 millivolts, so that's a gain of almost 35. So that's actually a little better than our calculated gain. So that looks really good. We're also at a DC bias point of right about 900 millivolts, just as we were designing for. So we're good to go there. And now we'll look back at the problem and make sure that we've answered all of the questions. So our power budget is 2 milliwatts. You can see that because we set this to be 1.1 milliamps and 1.8 volts. That gives us 2 milliwatts. And both transistors need to remain inactive. So that's one of the things that we always want to make sure we check at the end of every design anyway. So the active condition is VDS is greater than VGS minus VTO, and we can use our current equation to get that, which is 1/2 Kp times VGS minus VTO squared times 1 plus lambda VDS. We can generally neglect this here because lambda is 0.1, VDS is 0.9. That's much smaller than 1, so we're basically multiplying the rest of our ID equation by 1. So we can solve for VGS minus VTO, and for the NMOS, our Kp is 0.022, and that gives us a VGS minus VTO of 0.316, and for the PMOS, we'll label these here, that's N, this is P, and for the PMOS, Kp is 0.11, so that gives us VGS minus VTO of 0.447. BDS is our DC bias point, which we checked was at 0.9. So 0.9 is greater than both 0.316 and 0.447. So we're good to go there. So both of our transistors are inactive. The other thing that we always want to make sure we check at the end is that our assumptions are true. In this problem, we haven't made any assumptions, so we don't need to check anything there. And finally, this problem asks us what the output impedance is. So we need to know what the impedance is that we see from V out looking into the circuit. So we'll make it so we can see our circuit a little better here. So looking up, we're looking into the drain of the PMOS, and looking down, we're looking into the drain of the NMOS. So from our MOSFET equation sheet, looking into the drain, we see R0. So we see R0P looking up and R0N looking down, and those are in parallel. So we get R0P in parallel with R0N, and we already said at the beginning of this problem that R0N equals R0P because our lambdas are the same for this problem and the current going through both transistors is the same. So this is just 1/2 R0, and that equals R out. We can also see that we could have gotten that from here because of where our V out is, and looking into the transistor is the same thing that we did before. So that gives us the entire solution for this problem. We have a high gain that we were looking for, and we've biased both transistors to be inactive, and we solved for R out and followed the power budget requirement. So we're good to go.